Welcome to this celebration. Welcome to the celebration of the NANOGrav research team. Before we begin, a few housekeeping rules. This event is on the record and being live streamed on YouTube. If members of the media would like to request a more in-depth one-on-one interview with any of the members of the research team, please contact media@nsf.gov and they will coordinate details. My name is Michael Cabanero. I'm the director of the Physics Frontier Center program here at the National Science Foundation. We're here today to mark the occasion of the publication of new results from the North American Nanohertz Observatory for Gravitational Waves, familiarly NANOGrav. We're also here to describe those details and to discuss the significance of the new results. Of course, we're also here just to celebrate a remarkable scientific achievement that's been 15 years in the making. To help us celebrate this result, we're joined by a number of distinguished guests. Dame Jocelyn Bell Burnell, discoverer of the first radio pulsars, chancellor of the University of Dundee, joins us remotely. Kip Thorne, Emeritus Richard P. Feynman Professor of Theoretical Physics at Caltech, a Nobel laureate and world-leading expert in the study of black holes and gravitational radiation, has joined us here at NSF headquarters. We are also pleased to welcome Dr. Jim Jackson, Director of the Green Bank Observatory, Dr. Tony Beasley, Director of the National Radio Astronomy Observatory, and Dr. Adam Cohen, Director of Associated Universities, Inc. We had also hoped that Olga Figueroa Miranda, Director of the Arecibo Observatory, would join us today, but I think she had some problems with her flight and wasn't able to make it. Last, but certainly not least, we welcome Dr. Javier Siemens, Principal Investigator and Co-Director of the NANOGrav Physics Frontier Center. And he's brought along with him a significant fraction of the NANOGrav collaboration. I think a rather boisterous faction of the collaboration also. Now for a brief introduction to the panelists who are representing the collaboration here today. From left to right on the stage, Dr. Stephen Taylor, Chair of the NANOGrav collaboration, co-lead of the 15-year gravitational wave background paper, and an assistant professor at Vanderbilt University. Dr. Thankful Cromarty, Chair of the Timing Working Group, co-author of the 15-year timing paper, and Einstein postdoctoral fellow from Cornell University. Dr. Michael Lamb, co-chair of the Noise Budget Working Group, co-author of the 15-year detector paper, and a research scientist at the SETI Institute. Dr. Luke Kelly, chair of the Astrophysics Working Group, lead of the 15-year astrophysics paper, and an assistant adjunct professor at the University of California, Berkeley. Welcome, panelists. Oh, I forgot one. Sorry about that. Finally, Dr. Maura McLaughlin, co-director of the NANOGrav Physics Frontiers Center, a steering committee member of the International Pulsar Timing Array, and the Eberly Distinguished Professor of Physics and Astronomy, West Virginia University. I saved the best for last, so it's okay. Okay. And now I'm pleased to introduce Dr. Sean Jones, Assistant Director for the Directorate of Mathematical and Physical Sciences. Sean?
Great. Thank you, Mike. And I'm loving the energy that's here in the room. Good afternoon, everyone, and welcome. In 1995, the Hubble Space Telescope revealed the Hubble Deep Field, a tiny sliver of the night sky brimming with a veritable zoo of galaxies in various stages of evolution. In 2022, the James Webb Space Telescope refined and deepened that image, fantastically displaying galaxies more than 13 billion light years away from Earth. Aided by the state-of-the-art optical and infrared telescopes and decades of advancement in instrumentation and data processing, we perceive a static image of distant galaxies. Today's announcement shatters that perception of a static universe through the direct observation of gigantic gravitational waves washing across our Milky Way galaxy. spawned by cataclysmic events, including some from the most distant regions of the cosmos. These observations reveal a rolling, noisy universe alive with the cosmic symphony of gravitational waves. Or here.
Supermassive black holes lurk in the hearts of most galaxies, and galaxies grow by merging with other galaxies. When that happens, their black holes also merge and grow, becoming more and more massive over time. How exactly this happens is not fully understood, but the universe is telling us its secrets in gravitational whispers. We just have to listen. Just as sound waves are vibrations of air molecules, gravitational waves are vibrations in the fabric of space-time. When two massive black holes spiral toward each other, they produce gravitational waves that travel through the cosmos at the speed of light. If we imagine the universe as a grand symphony, these merging supermassive black holes are the bass players. As they orbit each other, these black holes play the deep bass notes that echo throughout the cosmic concert hall. But that's not all there is to the symphony. In the background is a faint but pervasive hum produced by the collective motion of massive objects throughout the universe, from the earliest moments of the Big Bang until now. This gravitational wave background is truly a harmony of space and time. NANOGrav is an NSF-funded collaboration of astronomers and astrophysicists. Our goal is to solve some of the deepest mysteries of the universe by studying the gravitational waves produced by these dancing monster black holes. These waves are light years long and can only be detected by the most extraordinary instruments. To measure these giant but subtle ripples in space-time, NANOGrav created a galaxy-sized detector using some of the most incredible objects in the cosmos, rapidly rotating neutron stars known as millisecond pulsars. Pulsars are the ultra-dense remnants left behind when massive stars reach the end of their lives and explode as supernovae. These pulsars are also cosmic beacons. They spin extraordinarily rapidly and with startling regularity, releasing pulses of radio waves with each rotation. Astronomers detect those pulses using giant radio telescopes. By monitoring the radio pulses from these ultra-precise cosmic clocks, NANOGrav can detect the slightest deviations in the regularity of their timekeeping, and these deviations trace ripples in space-time. This galactic scale detector is called a pulsar timing array. NANOGrav has now observed an array of dozens of pulsars for more than 15 years, and the results are astounding. We are finally hearing the faint background hum likely coming from in-spiraling pairs of supermassive black holes. With time, astronomers expect to pick out the individual instruments in this cosmic symphony, revealing unique insights into the evolution of galaxies and the history of the cosmos.
Excellent, excellent. Truly, truly amazing. Yeah, and great speaker as well. Yeah, and narrator. Truly, truly amazing. This achievement was made possible by an extraordinary collaboration involving more than 190 scientists from 70 institutions, the North American Nanohertz Observatory for Gravitational Waves, and NSF Physics Frontier Center. This project is a shining example of the transformative advances possible through long-term investment in NSF facilities and researchers and students at institutions ranging from small colleges to extremely large universities all across this great country. The National Science Foundation is proud to support daring team efforts like NANOGrav to expand our knowledge for the benefit of society. With us today are 5 members of the NANOGrav team who will describe their recent published results. We'll start with the chair of the NANOGrav collaboration, Dr. Stephen Taylor. Dr. Taylor?
Thank you, Sean. Distinguished colleagues, honored guests, and for all those following along at home, it's a pleasure and relief to finally share the following news with you. Over the last 15 years, we, the NANOGrav collaboration, have been on an audacious mission to find the low-pitch hum of gravitational waves coming from all over the universe, washing through our galaxy to stretch and squeeze space-time between the stars. Well, now we're here today to finally tell you all that patience is a virtue. Friends, our hard work has paid off, and we're really doing it. Even more excitingly, this is all the culmination of a coordinated process with our international colleagues using telescopes in Europe, India, Australia, and China. In the following, I'd like to tell you 3 things. First, about our detector, then about how gravitational waves imprint signals in our detector, and finally, how we found evidence for gravitational waves. First of all, we didn't do any of this just by building an instrument on Earth or even in the solar system. In fact, we harnessed a collection of astronomical objects in our neighborhood of the Milky Way to act as one big gravitational wave antenna. These objects are pulsars, and they're about as close as we can get to clocks in space. Pulsars are these super dense remnants of stars that have exhausted their fuel and contracted inwards, squeezing about the mass of the sun into the size of a city. And if you set that object spinning hundreds of times a second, blasting out beams of radio waves, you've got yourself a pulsar. Now, those radio beams I mentioned wash across Earth every time the pulsar spins around, and we measure this as regular pulses in our radio telescopes. In a way, these pulses are like the ticking of a clock out in space. And this makes pulsars perfect to study phenomena associated with Einstein's relativity theories. And while these pulsars are extraordinary objects in their own right, to us, they are the components of our vast galaxy-wide gravitational wave antenna. This is galaxy-scale hacking. Now, when gravitational waves cascade through the galaxy, they warp space-time between the pulsars, causing the ticking of these cosmic clocks to change in a predictable and correlated way among the numerous pulsars that we monitor. Without gravitational waves, the ticking rate of these pulsars should be completely independent, with 0 correlation. Remember, these pulsars are separated by hundreds to thousands of light years, after all. But with gravitational waves warping space-time in the galaxy, and with Earth as the common endpoint of all of our pulsar observations, Einstein's theory of general relativity predicts a unique pattern for the correlation in those ticking rate changes between pulsars spread across the sky. Here is that pattern. This is the unique fingerprint of a background of gravitational waves, and there's nothing else we know of in the pulsars, in the intervening gas, or on Earth that can produce this pattern. Now, with almost 70 pulsars used in our gravitational wave search, this gave over 2,000 ways of pairing up the pulsars in a correlation analysis. For each pair, separated on the sky by a known angle, we measured the correlation of how much the ticking rate of their pulses are changing and offset from model behavior. And in what I show you next, we've distilled all that information into some average correlation measurements in 15 points between 0 and 180 degrees of pulsar sky angle separation. This makes it a ton easier to visualize, even though our detailed analyses don't require this. You know, I think I've dragged this out long enough, but that gives you a taste of what it's like to wait 15 years, okay? Here is what NANOGrav sees. Gorgeous. This pattern, imprinted in data from vastly separated pulsars across the galaxy, shows incredible agreement with the fingerprint of gravitational waves described by general relativity. A lot of information is hidden when we visualize our data this way, but our detection statistics show the chances of nature delivering these results without gravitational waves being present is less than 1 in 1,000, and in some of our tests, 1 in 10,000. That would be like trying to flip a coin and get heads 10 times in a row to 14 times in a row. And this significance will march higher in the future. NANOGrav is a gravitational wave detector and collaboration of people that intersects many different disciplines. My colleagues are next going to describe how we go from observing pulsars to modeling noise, finding evidence for gravitational waves, and ultimately constraining the astrophysics of supermassive black holes and theories of the early universe. It's my pleasure to hand over now to Dr. Thankful Cromarty to describe NANOGrav's pulsar timing campaign. Thank you.
Thank you so much, Steve. So, as Steve just mentioned, our detector isn't something that you could build in a lab or even launch into space. It's closer to the size of the galaxy, and it's made up of dozens of rapidly rotating neutron stars called millisecond pulsars. These objects are second only to black holes in density. They spin faster than your kitchen blender, and they have magnetic fields almost 1 billion times stronger than the Earth's. As a pulsar rotates hundreds of times a second, the radiation beam coming from its magnetic axis sweeps across our line of sight, giving the appearance of a pulsating star. Pulsars were first discovered in the late 1960s by Dr. Jocelyn Bell Burnell, and we are so honored to have Dr. Bell Burnell with us online. Thank you so much for joining. Their pulses arrive at such regular intervals that scientists initially joked the signal might be coming from aliens. In short, pulsars are unfathomably interesting cosmic clocks. We use a technique called pulsar timing to study them, which involves crafting a model that can predict the time of arrival of each and every pulse coming from a pulsar going far into the future. These timing models take into account every imaginable factor that impacts when pulses arrive at the Earth, from movement of solar system bodies to binary orbital motion, and even to the interstellar medium, which is the medium inhabiting the space between us and our pulsars. For gravitational wave experiments like NANOGrav, the precision of our pulsar timing has to be better than a microsecond. For some of our sources, we know when each pulse will arrive to a precision that rivals atomic clocks. Pulsars can be studied at a wide range of wavelengths, stretching from the least powerful radio waves, which are around the same frequency as your FM radio, to extremely high energy gamma rays. But their emission is strongest at low frequencies, and so we traditionally study them using radio telescopes. NANOGrav's been lucky enough to use some of the world's largest and most cutting-edge radio telescope facilities. These include the 100-meter Green Bank Telescope in West Virginia, the 300-meter Arecibo Telescope in Puerto Rico, and the 27, 25-meter dishes of the Very Large Array in New Mexico. So what's this detector actually made of, and what do our timing data even look like? The more pulsars scattered across the galaxy that we can time, the more sensitive to gravitational wave signals we become. And for that reason, NANOGrav's been feverishly adding pulsars to the array ever since the very beginning. Now let's take a look at the history of NANOGrav's data set. Our first data set, which we refer to as the 5-year, included approximately 5 years of data for 17 millisecond pulsars, timed using the Green Bank and Arecibo radio telescopes. The 9-year data set had 37. The 11-year data set had 45 pulsars, and the 12.5-year data set had 47. Now today, we're sharing with you the NANOGrav 15-year data set, which includes more than 15 years of timing for 68 millisecond pulsars. For the first time, we're also including data from the Very Large Array in our release. These data, as well as the brand new pipeline we've been working hard on, are available publicly starting today. Now, there's an enormous amount of science that we just sort of get for free from timing dozens of pulsars over a decade and a half with the world's best radio telescopes. With this much high-quality data, we've been able to do large-scale studies of our pulsars as astrophysical objects in their own right, instead of mere tools for gravitational wave detection. We can learn about their astrometry, which is a pulsar's motion through the Milky Way, probe the structure of the interstellar medium between the Earth and each pulsar. And for our pulsars that are in orbit with another star, we can sometimes measure the pulsar's mass and the mass of its companion using general relativistic effects. This last point is notable because precisely measuring pulsar masses helps us understand the fundamental nature of the extremely dense matter deep inside the cores of neutron stars. Now, I'll spare you from me droning on about how cool this is, but the takeaway is basically that once again, our astrophysical clocks can help us conduct science that just can't be done in an Earth-based lab. So the data in this release is the culmination of countless hours of work by NANOGrav members at all levels, including many students. Without the team's collective ingenuity and dedication, creating such a massive data set wouldn't have been possible. So with that, it's my absolute pleasure to introduce my colleague, Dr. Michael Lamb, who's going to talk to you in more depth about our detector.
Thanks to the hard work of so many people, we built our galaxy-sized gravitational wave antenna using almost 70 millisecond pulsars spread across the Milky Way, along with radio telescopes here on the Earth, and using well-tested techniques approved upon for decades. But even so, how do we know our detector is good enough to find the incredibly tiny signals produced by gravitational waves? Millisecond pulsars are the best astrophysical clocks we have, but they aren't perfect. At a very small level, they will wobble as they rotate, causing the ticks of our clock to arrive slightly early or a little late over time. Then, the pulses are delayed and distorted as they travel through thousands of light years of gas in the Milky Way. And finally, while we make the best measurements we can here on the Earth, an example of simulated data for one pulsar shown here, these aren't perfect either, so we have to properly calibrate our data and clean out radio interference in our measurements. To make matters more difficult, each Earth-to-pulsar arm of our detector is unique. And unlike most detectors we build here on the Earth, we can't go to the pulsars to measure or tweak them. Our goal has been to extract the tiny signal from gravitational waves from many different sources of noise in our detector that mask that signal. It's a really challenging problem, as gravitational waves are constantly passing through our detector, and we can't turn the signal off in order to determine how our detector behaves on its own due to only noise. Many of these noise effects can be much stronger than the gravitational wave signal we're investigating, hundreds or even thousands of times stronger. Some of these effects change depending on the radio frequencies we observe at, whereas gravitational waves are the same strength regardless. So that's one of the many ways we can pull the signal out from the noise. We needed to measure precisely when pulses arrived at our telescopes to within 100 nanoseconds or better to be sensitive to gravitational waves. Over many years, we have performed many careful analyses to uncover the sources of noise and learn how the characteristics of our signal differ from the noise sources. The statistically common signal we extract from all of our pulsars has an astronomically small chance to be produced from the individual pulsars alone. As with our previous data set, we have enormous evidence for a signal with common statistical properties. In each pulsar, the signal of a gravitational wave background may appear as a random oscillation over long timescales, but it imprints a unique pattern between pulsars that we can extract from noise. One of the benefits of our technique relies on the fact that our gravitational wave signal has a very special correlation when you analyze the data from different pulsars together. When the correlation between two pulsars is positive, that means the radio pulses are arriving either both early or both late. When the correlation is negative, then the radio pulses will arrive early in one and late in the other. Notice how Einstein's theory of general relativity predicts that the correlation in the time of arrival offsets starts positive when the pulsars are close to each other on the sky, becomes negative, close to 90-degree separation, then goes positive again when the pulsars are on opposite sides of the sky. Analyzing our 15-year data set, we find strong evidence of this correlation pattern, something like a 1 in 1,000 to 1 in 10,000 chance that the correlations would have been produced only from noise, depending on the analyses we perform. We find that these gravitational waves have an incredibly small strength, so small that they cause space-time to change by 1 part in a quadrillion. Next, Dr. Lou Kelly will talk about what sources will cause gravitational waves of these low frequencies and these tiny amplitudes.
Thank you so much, Michael. And as Michael pointed out, the amplitude of these signals is 1 part in a quadrillion. That's 1 part in 1,000,000 billion. This corresponds to a measurement precision of about 100 nanoseconds over the course of our 15 years of data. And now, while this has been an incredibly challenging signal to detect, it's actually booming loud in terms of gravitational waves. But because we're in the early days of measuring this signal, we can't yet confirm what sources are producing the gravitational waves. We believe, however, that they're produced by some of the most rare and most energetic objects in the universe, binary systems of two supermassive black holes, also the coolest objects in the universe. We know that these gigantic black holes lie at the centers of large galaxies distributed throughout the universe. While the black holes themselves are only as large in size as a solar system, they have masses as high as billions of suns. Now, as galaxies grow over cosmic time, they merge with other galaxies, and this provides the opportunity for two supermassive black holes to come together. For decades, astrophysicists have theorized that binary supermassive black hole systems could then form and produce exactly the types of gravitational wave signals that we're seeing. Despite years of searches using traditional telescopes, no supermassive black hole binary has been fully confirmed, although a handful of very compelling sources have been identified. The signal we're measuring wouldn't be produced by a single black hole binary, but instead by large numbers of supermassive black hole binaries all across the universe. Each of those binaries produces a slightly different frequency or different tone of gravitational waves, which together produce a symphony or a hum that we call a background. Using new theoretical models, we have simulated billions of supermassive black hole binaries, predicted the gravitational waves that they would produce, and compared that to the signals that we're measuring. I want to share with you those results. Here, the vertical axis shows the amplitude of the signal, corresponding to how many binaries are out there and how massive they are. The horizontal axis corresponds to the distribution of gravitational wave frequencies, how many binaries are emitting at different tones. Models appearing towards the right correspond to binaries evolving in isolation, while models showing up towards the left correspond to binaries that are interacting strongly with their host galaxies. Here in orange is the classic, simplified model of binaries that expects gravitational wave signals to show very little interactions, binaries evolving in isolation. In blue are new, more comprehensive models of binaries, starting when galaxies merge and evolving all the way down to the small separations at which those black holes can produce detectable gravitational waves. These models include interactions with the gas and stars and the nuclei of each of their host galaxies and produce much broader expectations. Finally, this is what we measure from the NANOGrav 15-year data. And if we zoom in, we can see that the data is consistent with both models. However, there is more overlap with the blue interacting simulations, hinting that perhaps binaries may not be evolving in isolation, and even in the strongly gravitational wave emitting regime are interacting. In either case, the signal that we're measuring is a bit louder than we expected, which means that supermassive black holes would need to form binaries relatively frequently and/or with quite high masses. We cannot yet confirm whether or not supermassive black hole binaries are producing the gravitational wave background. But if it is produced by binaries, then these models offer tantalizing hints about their properties. We'll need to keep taking data, continue to develop new models and methods to find out more. Other kinds of sources have also been proposed as the origin of the gravitational wave background. NANOGrav scientists who study the fundamental properties of the universe have shown that our measurements could also be consistent with signs of cosmic inflation, the rapid expansion of the universe soon after the Big Bang. They may even be signs of new, as yet undiscovered, fundamental physics. The way we'll be able to determine if these gravitational waves are coming from binaries or coming from new fundamental physics is by mapping where the gravitational waves are coming from. Just like we can create maps of the night sky using electromagnetic radiation, we can now create maps of the sky using gravitational waves. As our sensitivity continues to improve, we expect to be able to detect whether the gravitational wave background is stronger on one part of the sky than another, whether there are more instruments from one part of the sky or another. We believe that this would be a definitive indicator that supermassive black hole binaries produce the gravitational wave background. If it is binaries, then as our sensitivity continues to improve over the next few years, we'll be able to resolve the structure of that gravitational wave sky and eventually be able to detect individual binaries that are loud enough to resound above the background. This would be a particularly exciting opportunity for multi-messenger astrophysics, in which both gravitational waves and electromagnetic signals can be observed from the same sources. Once this happens and we're able to see and hear these sources at the same time, we would be able to make unprecedented measurements about supermassive black holes and answer fundamental questions about where they come from, how they evolve, and how they interact with the galaxies that they live in. Next, one of our great founders, Dr. Maura McLaughlin, will tell you more about our collaboration.
Thank you, Luke. Hi, everybody. We hope that you are now as excited about this new field of low-frequency gravitational wave astrophysics as we all are. I'm going to wrap things up by discussing our collaboration and our funders, the international landscape of our project, and I'll close with a look to the future. None of what you have heard today could be achieved without many years of sustained effort on the part of a lot of people, most of whom are not up here on this stage or even in this room. The idea of using pulsars as gravitational wave detectors was first proposed in the late 1970s, and worldwide pulsar timing array collaborations started to form in the mid-2000s. NANOGrav started as a group of about a dozen scientists in 2007. We've now grown to 194 members, including 77 graduate students at over 80 institutions throughout the United States, Canada, and 12 other countries. We've also involved hundreds of undergraduate students and thousands of high school students in searching for pulsars, which directly increases our sensitivity to gravitational waves. And in fact, some of these students are watching right now from Pulsar Camp in Green Bank, West Virginia. So hey guys and girls. These results would not be possible without each and every one of our NANOGrav members. And I am personally so grateful to work with the most amazing and wonderful group of people in the world. We are very thankful for the US taxpayers who are watching this, as you ultimately support us through National Science Foundation funding. We got our start with an NSF award in 2010 from the Partnerships for International Research and Education program. And then we were thrilled to be named an NSF Physics Frontier Center in 2015. NSF funds 10 of these PFCs established to foster major breakthroughs at the intellectual frontiers of physics. And we are just so honored to be among this group. NANOGrav is also supported by the Moore Foundation and the Canadian NSERC and CFAR funding agencies. This result would, of course, also not be possible without NSF's significant investments in the Green Bank Telescope, the Arecibo Observatory, and the Very Large Array. The incredible staff at these observatories have worked tirelessly for decades to benefit not only our science case, but many, many others. Thank you. So what's next? Well, this is not at all the end of the story. This is just the end of the beginning. NANOGrav is already working on our next data set, which will have 17 to 18 years of pulsar timing data. And we expect that the evidence for the gravitational wave background that we have found in this data set to be much stronger in that one. And we're going to become even more sensitive with time as we increase the length of our data set, as we add more pulsars to our array, and most importantly, gain access to bigger and better new radio telescopes with more dedicated NANOGrav observing time. In addition, we are very proud to be a member of the International Pulsar Timing Array. The IPTA was formed 15 years ago and consists of pulsar timing array collaborations worldwide. Today, groups in Europe, Australia, India, and China have also released results from their most recent gravitational wave analyses. And we all see similar features in our independent data sets, which of course is reassuring and also incredibly exciting. Furthermore, through this collaboration, and partially supported through an NSF ExcelNet Award, we are working with colleagues around the world to combine our current data set with pulsar timing data sets from large radio telescopes in Europe, India, South Africa, and Australia to form an uber data set that will be much more sensitive than any of the individual data sets alone. We aim to announce results from a gravitational wave analysis of this combined IPTA data set within the next year or two. This analysis will be truly transformative. It should result in a significant detection of this gravitational wave background hum. In this combined IPTA dataset, we may even detect our first individual supermassive black hole binary source, and likely also be able to observe it with electromagnetic telescopes at optical, X-ray, or other wavelengths, truly ringing in the era of multi-messenger nanohertz gravitational wave astronomy. Ultimately, we will produce an incredible map of invisible gravitational waves from gargantuan black holes spread across cosmic time. We will also probe some other exotic and less well understood sources for this background. We are so thrilled that you are joining us on this journey. Thank you. At one time, all we knew about the universe resulted from visible light, light we can see with our eyes. Then when radio and X-ray and gamma ray telescopes came online, we learned so much about the universe that we just couldn't have imagined before, like the radio pulsars that Jocelyn discovered over 50 years ago. Now, we can only dream about what we'll learn with observations in a different part of the gravitational wave spectrum from the LIGO detections that visionaries like Kip made possible, with continued investment in our science and in large radio telescopes. And we are certainly expecting the unexpected. All we have to do is keep listening. Thank you.
Let's see if I can avoid missing any more scripted lines here. So that concludes the presentation from the NANOGrav team. Thank you very much. Wonderful presentation. Before we begin our panel discussion, I'd like to address a question to Dr. Bell Burnell. Are you there, Jocelyn?
Yes. Can I be heard?
Yes, we can hear you fine. So Jocelyn, when you discovered the first radio pulsars, did you realize how important these objects would become to the future of astronomy and gravitational physics?
Well, we could see them had great potential because of their timing accuracy. But I guess we weren't thinking in terms of gravitational radiation back in the late 1960s.
I see. Thank you. I'd now like to welcome Professor Thorne to the stage, please. Kip, I will. Yep. Okay. The microphone's up here on the stage. Kip, of all the potential future NANOGrav observations, which type of phenomena is the one most interesting and exciting to you?
Well, I must say that the prospect of seeing can you hear me? Okay. The prospect of determining the properties of these supermassive black hole binaries, the largest, the heaviest black holes in the entire universe, is really exciting. But to me, there's something even more exciting that's on the horizon, perhaps for NANOGrav, very probably for gravitational wave astronomy generally in the decades to come. And that's to use gravitational waves to probe the birth of the universe. according to everything we know observationally and theoretically, the universe was born in a Big Bang singularity that was governed by the laws of quantum gravity, laws that are not well understood. And that singularity, however, had to give rise to gravitational waves. The laws of physics demand that that was the case. And whatever form of gravitational waves they gave rise to had to be amplified by the early inflationary expansion of the universe. And so those gravitational waves must carry a mixture of information about the birth of the universe itself, about the laws of quantum gravity that controlled the birth of the universe and the creation of the waves, and about the inflationary expansion of the universe, all convolved together in a complicated way. So to me, the holy grail of this field in the long run is to explore the birth of the universe and extract that information that's carried by the gravitational waves. Now, the conventional wisdom of theoretical physicists says that those gravitational waves are too weak for NANOGrav to see. But in my 60-year career, 60 years as a physicist, I have seen conventional wisdom fail spectacularly on several occasions. And so I hold out the hope that some of the gravitational waves that NANOGrav is seeing are primordial gravitational waves from the Big Bang. But even if they're not, I am still tremendously excited by the science that we have heard about today that will come as the data get better, as statistical analysis techniques get better, and as the various detailed properties of these waves are explored. And we learn so much more about the heaviest black holes and black hole binaries in the universe.
Thank you, Kip. So now we have several questions for the panel. The first one really touches upon what Kip just said. So let me ask the panel, you alluded to a variety of alternative sources of the gravitational wave background. Could you comment on the potential cosmological origin of these signals and what's more likely? Are your current signals more likely cosmological or binary black hole in origin?
Yeah, sure. That's a great question. So in addition to the supermassive black hole binaries that could be formed in this signal, there are theories of the early universe that could produce a variety of different types of gravitational wave signals, like Kip referred to. Not only primordial gravitational waves from the post-inflation era, but also phase transitions in the early universe that could give rise to different signals. Those phase transitions give rise to exotic things like cosmic strings and domain walls, which themselves can source gravitational waves. These are all really exotic and interesting phenomena, and we don't know yet the composition of our signal. It's most plausibly supermassive black hole binaries, but I'm also hoping that some of the signal really is an echo from the earliest parts of the universe.
Okay. Thank you. The next question, can NANOGrav observations teach us anything about dark matter?
Thank you. Yes, I think they definitely could. So in particular, there are models for dark matter like axion or fuzzy dark matter that also have predictions for producing gravitational waves. And they're in one of the NANOGrav papers, we do place stringent limits on some of these models that are absolutely competitive amongst the most stringent limits that can be placed on things like dark matter in addition to models of the early universe. So I think it's extremely exciting that while in the most mundane case, we're thinking about supermassive black hole binaries, we are also doing this incredibly precise measurements about fundamental physical properties of the universe at the same time.
Thank you. The next question would make a good Astronomy 101 final exam question. So astronomy professors out there, listen up. You describe gravitational waves as gigantic, very, very tiny, and booming all at the same time. What are you talking about?
Yeah, that's a great question. For us in our measurements, the gravitational waves have an extremely long period, very low frequencies. So that means that the wavelengths of the gravitational waves span many, many, many light years. So they're long in that sense. But the amplitudes of those gravitational waves, how much they're actually changing space-time, are themselves very tiny. We mentioned about 1 part in 1 quadrillion. However, compared to previous models of the expected gravitational wave background, that signal is booming loud compared to what we thought we would see. And so we're very excited that even though they're very, very tiny, the universe is talking to us.
Thank you for that. Next question. You mentioned that the next step is to combine all the data sets from all the international group. How will this lead to new constraints in physics beyond the standard model?
Yeah, so right now we are working with our international colleagues on what we're calling DR3, or the third data release of the International Pulsar Timing Array. And this data release will be more sensitive than any of the international data sets because it will have more pulsars, it will have more telescopes, it will have more radio frequencies, it will have more observations. And whenever we add more data, we get a much more sensitive pulsar timing array. This process isn't complete yet, so we can't predict, like right now, like exactly what boon in sensitivity we're going to see from this combination, but it should be significant. And with every increase in sensitivity, we'll be able to say more things, to discriminate the spectrum, which is basically the power of the gravitational waves versus gravitational wave frequency for different models. That's really what we want to do. We want to be able to look at like how bright is this gravitational wave signal across a range of gravitational wave frequencies. And the better we can constrain that spectrum, the better we're going to be able to discriminate supermassive black hole binary origins from more exotic origins. And so this International Pulsar Timing Array data set, which has a very long time span and increased sensitivity, is going to be really, really, really exciting.
Thank you. I have a couple of personal questions I want to ask. NANOGrav is a very large and far-flung collaboration. Judging from this gallery, it's a very tight-knit collaboration. What is the glue that holds this collaboration together?
I'll take a shot at this. And I'll just say, first of all, I'm so grateful to work with everyone in this room and everyone watching online. I think maybe it's not the glue, but the fact that everyone is so respectful of each other and we're all motivated by the same incredible science. I think that's the glue. That's the main thing. We all want the same thing, but we all want to be good collaborators and friends and colleagues. I don't know. Yeah, we're excited about what we do, and we're also excited to work with the people that we work with. So it's really an honor. It's a big deal.
Good answer. Thank you. So could you describe other ways in which NANOGrav is having an impact beyond the amazing scientific results?
There's some science we stumbled into along the way that we had no idea we would find. A few years ago, we were analyzing a data set and found that the accuracy limits we were hitting were testing and stressing models of the solar system. We have to reference everything back to the center of mass of the solar system, which is not a physical point. It's just a center of mass. So we had to update that. We were talking with the people who build these, and we're finding out that we had the greatest demand for this accuracy, needing to know the center of mass of the solar system within 100 meters, like the length of a football field, something like that. So it's extraordinary. We had to inform this, update it along the way, incorporate it into our search analysis. So we were updating the solar system as well as searching for noise in all the pulsars and finding gravitational waves. So it was extraordinary. There's also some fantastic individual pulsar science that we can do that Thankful is an expert on.
Okay, we can move on to another question. This is actually a follow-up question for Kip. How do you think these results will affect the gravitational wave astronomy landscape and discovery space?
So there are four different frequency bands in which we expect humans to be seeing gravitational waves by something like the late 2030s. The high frequency band where LIGO first discovered gravitational waves, where there are now several different detectors around the world operating. That's what the gravitational waves have periods of a fraction of a second, something like typically 100th of a second. Then there is a frequency band where several space-based detectors are likely to operate in the 2030s and beyond. LISA is the most famous of these. That's with periods that are a few minutes to hours. There is the band that we are talking about today with periods of years that NANOGrav is operating in, and also the other collaborations elsewhere in the world. And then there is the extremely low frequency band of periods of millions of years. Now that's rather long compared to a graduate student lifetime. So graduate students don't sit there and analyze data and watch the waves come in. Rather, you look for patterns of polarization of cosmic microwave background on the sky that are put onto the microwave background by the gravity waves. So patterns on the sky. And so we have these four different bands. And when we can, by the middle of this century, when we have all four bands in operation, this is going to be tremendously exciting. And the science that's going to come out is really, I think, going to be phenomenal. It's like going from Galileo's first pointing telescope at the sky and seeing the four moons of Jupiter to modern electromagnetic astronomy. This is the beginning of that process for gravitational wave astronomy.
Okay, thank you. Do we have time for one final question? Yeah. And the last question then is, how do we know that this won't be a bicep 2-like result?
So, of course, this is something that we have thought very long and very hard about. We do not want to be another bicep 2. And for those folks at home, this was an experiment that announced a big discovery, and it ended up not being real. And so we of course, do not want to be in that position. We are very confident that we are not going to go down that path. The first reason for that is that in our last data set even, we saw a very, very strong source of common noise among all the pulsars in our array. We couldn't yet see these very special spatial correlations, but we see a very strong source of noise that can't be ascribed to any other source. So even a few years ago, we were pretty sure that we had gravitational waves in our data set. There was basically nothing else that could really create that signal. On top of that, this same source of common noise was seen in the data sets in all of our international collaborators. So they all saw this exact same, consistent source of common noise. Now we have these spatial correlations. The spatial correlations, by chance, in just our data set, are significant at a 1 in 1,000, 1 in 10,000, random chance level, which is pretty darn good. And similar signals are seen in data from a combined European-Indian pulsar timing array analysis, a Chinese pulsar timing array analysis, and an Australian pulsar timing array analysis at different levels of significance, but they are all similar. So this makes it extremely unlikely that this is just some random fluke in our data. We are very confident.
Thank you again, panel. I'd like now to ask Sean to provide us with some closing remarks.
Thank you, Michael. Let's give this panel a round of applause. Yeah, keep it going. Yeah. And that's for you in the room as well, and all the collaborators that are online. Thank you so much. This is phenomenal. And to quote one of our panelists, this is cool. So thank you to all of our speakers for this report. And I want to also thank the organizers for this event, for this celebration. And I want to thank Michael for his stewardship for today's event and for the NANOGrav Physics Frontier Center, but also our co-director here at the National Science Foundation, Dr. Kathy McLeod, wave, for all of your tireless and hard work as well as co-director for the Physics Frontier Center and for NANOGrav in particular. You're welcome. On behalf of the National Science Foundation, I'd like to congratulate the entire NANOGrav team on the publication of this hard-earned result. The Physics Division, the Division of Astronomical Sciences, and the Directorate of Mathematical and Physical Sciences are pleased to support foundational research at the frontiers of physical science and are delighted to advance explorations into the wonders of the universe. And we don't do this alone. As mentioned, the Partnerships in International Research and Education, PIRE, NSF ExcelNet, and external agencies and foundations have all contributed to these NANOGrav advances. Now, I'm looking forward to future results, holding you to that, in this important new field of low-frequency gravitational wave astronomy and what it will teach us about the evolution of our universe. And of course, I look forward to hearing more music from the Cosmic Symphony. Thank you, everyone. Congratulations. All right. Fantastic. Yeah, great job. Great job.